So the first question says the following table shows the results of a random sample of, it was supposed to say 250 people, and then it asks you some questions. It also gives you some additional information that says that given that a person is from Quebec, the probability that the person does not have their license is 0.25. So if we're looking at our table, it's telling us that given that the person is from Quebec, so we start off, we're looking at the Quebec line of the graph. But because we don't have any information in that graph yet, we have to figure out how many people are from Quebec. So we've got 250 minus 150, which gives us 100. Now we can go ahead and use that piece of information that the 0.25, so it's 0.25, it's 25%, which translates into 25 people. 25% of 100 is 25. So now we've got that information. How many people from Ontario do not have a license? So we can then go through process of subtraction. We can figure out that there are 55 people. So we just asked for how many people. They didn't ask you for a probability, so it was just a matter of digging up, going that far and figuring out the number. Then it says, if you randomly select a person, what is the probability that you get a person from Quebec who has a license? So we want to know the probability that they're from Quebec and have a license, and we're dealing with just randomly selected from the whole population. So we need to calculate that. So we've got 100 minus the 25 leaves us with 75 in Quebec have driver's licenses. So if you randomly select a person, what is the probability? Now, this time we're being asked for a probability that you get a person from Quebec who has a license. So the probability is 75 out of the 250, which you can reduce down to 3 out of 10. Dividing each part by 25, you end up with 3 out of 10. Now we're into the part that everybody loves so much. You have to look at these and just think of them as puzzles. And if you're trying to solve puzzle, you kind of break it down into smaller pieces and solve one piece at a time. So to solve this one, the first thing I'd be looking at is maybe I'd look at this centerpiece here, because that's it's not quite the centerpiece, but just look at that one piece and say, how do I get that? What is that? Well, I'd start off by saying, well, it's the intersection between B and C, right? It's the overlapping area there between B and C, but it doesn't include the spot in the center. So in order to get rid of the spot in the center, I do an intersection with A. So I want everything that's in B and C, so it has to be in both places, but it's not in A. So this says it's in B and C, and it's not in A. So remember, whenever you've got the complement of something, complement of a set, you can always think of it as not. So we've got that. That's the center. That's that one smaller piece. But now we need to figure out the bigger chunk. So that one obviously makes sense. It's going to start with A, but it's missing this chunk here. And that chunk there is where it overlaps with C. So similarly, we can say that it's A and it's not C. So we've now described the two pieces separately. We want to kind of add them together. We don't use addition when we're doing sets like this. We use the union symbol. We do an OR. With that, we've got the set builder notation that describes the two pieces all together. So we did the two pieces separately, and then we used a union to add them together. All right, so moving on to the next one. We've got similar kind of scenario. So we actually start off with the same piece that we had in the last one. So the easiest thing to do would be to say, okay, well, we'll just start with that. That is B intersection with C intersection with not A. And what about this piece over here? We can say, well, again, starting with A, but this time it doesn't have any of the B and it doesn't have any of the C. So it's A and not B and not C. Then we want to add those two together, so we join them with a union. That gives us the effect of sort of adding them together. Okay, so same thing here, right? We're starting off with A, so it's everything that's in A, but it has to be in A and not in C and not in B. So by intersecting with the complements, that's how we remove them from the solution. Now part 3. This one's a little bit different now because we've got the area outside of the sets being brought into the situation. So whenever we see that, we know we're going to be working with a complement of some kind. The easiest way to do this one is to look and see, well, we've got the intersection, but it's in white, and we want whatever's in green. But it's everything that's not the intersection. So that allows us to then say it's the intersection of A and B, but then the complement of whatever that is. So by doing it this way, we've identified the easy part because it's very easy to see that that's the intersection. And then we say it's everything that is not that by putting quotation mark on the top. So we define that as the complement. So that's one way of doing it. The other way is to say, okay, well, we know it's going to be some kind of a complement. It has to be, so we're going to say if we looked at A, we say, well, it's everything that's outside of A for sure, right? Everything outside of A is part of the solution. But then everything that's outside of B is also part of the solution. So if we've got everything outside of A added to everything that's outside of B, then we could also write it out as complement of A union with the complement of B. So it's everything that's outside of A plus, which is sort of adding to it. We're expanding, we're making a bigger set. Everything outside of A added to everything that's outside of B. So it's complement of A union with complement of B. Next one, right in the center. So we'll start with that piece. I think most of you are pretty good at figuring out that that's A intersection B intersection C. So that part's pretty easy. Now we've got everything that's outside of all the sets. But unlike the previous one, where we actually went inside here, this time it stays outside of both the sets, or all three of the sets. So this time, again, we know because it's outside of the sets, we're going to be working with the complements. So we say it's complement of A. I'm figuring it's going to be, it's outside of B and it's also outside of C. So the only thing you need to resolve then is, are you intersecting or complementing those? In this case, because it doesn't close up inside anywhere, it doesn't go inside any of the sets, that tells us that it's got to be an intersection. So it's the part where everything that's outside of A intersects with everything that's outside of B, and all of that intersects with everything that's outside of C. So by doing those intersections with the complements, it means it's outside of everything. And you do the intersection, and that's what you get. And we join them together with a union. So hopefully, I know some of you seem to be getting these now. If you're not, I wouldn't lose too much sleep over it. I put some on here that were harder than what you're going to have to do on the quiz. I wanted to kind of push you guys a little bit to try and get your brains going there. It's a very small part of the quiz to be able to do those sets, do the set notation or the set builder notation. So don't lose too much sleep if you're not getting those. Okay, question 3. So the number of people on a development team who know specific programming languages are represented in the diagram below. What is the probability that the person you select will be not a PHP programmer? So we have to look at PHP, and we know we're going to be outside. Everybody is outside of PHP. So that means we've got 1, 10, 15, 12, and 5. We add all those together, and we end up with 142 out of 200, which we can reduce down to 71 out of 100, which of course you can convert to a decimal if you want to, as 0.71. Don't have to, but you may. Part B says, what's the probability that the person you select will know PHP and HTML? So that's the intersection between them. They know both things. They know both PHP and HTML. So you can add those together, the 35 and the 5. You get 40 out of 200, which is equal to, reduce that down to 4 out of 20 or 1 out of 5, which is 0.2. Now the people who know, I would say, know HTML and JavaScript. So they know HTML and JavaScript. So that's very similar to the last one. 15 plus 5 is 20 over 200, or 1 out of 10, which is 0.1. Now, a person who doesn't know PHP, so they have to be outside of PHP or HTML. So that means they also have to be outside of HTML. So if they don't know PHP or HTML, that leaves us with 5 and 12. We got 17 out of 200. Or if you reduce that down to decimals, 0.085. Last one, somebody who doesn't know PHP, but will know HTML and JavaScript. So they don't know PHP, but they know HTML and JavaScript. So they have to know both of those. So we end up with the 15 out of 200, which is equal to 3 out of 40, or you could convert it to decimals of 0.075. Question number 4. So similar to the last one, I'll go through it a little bit quicker as a result. So this time they're saying, okay, we're looking for the probability that somebody speaks only French. So only French is 45 out of the total. And in this case, the total, if you add them all up, if we look at the sample space, it is 222 people that were sampled. So it's 45 out of 222, which if you do the math, you can convert it to a decimal if you choose to, 0.2027. Part B says they speak French and Spanish. So French and Spanish, 25 plus 7 gives us 32 out of 222. If you want to convert to decimal, you've got 0.1441. Okay, so that's really what the next one gets to. They speak French and Spanish, but not English. So that's now where you've got the 25 out of 222, which if you want to convert to decimals is 0.1126. Now they speak only 2 languages. So remember, the people in the center, they speak 3 languages. So the people who speak 2 are the intersections without the middle. Add all of those up, and we get 25 plus 20 plus 15, which gives us 60 out of 222. And if you want to convert it to decimals, it's 0.2702. And finally, they speak only 2 languages, and one of their languages is English. So if they speak 2 languages and one is English, then it's just those 2 intersection points that we're talking about. So we end up with 35 out of 222. And if you do it in decimals, it's 0.1576. Then we move on. So we start off, we're told we have 3 groups: single parents, people with income less than 40,000, and people who live in Gatineau. So let's take a look at the single parents, and we'll put that on our graph, our diagram there. So remember, I can't put it in here because I don't know how many of them go there, how many of them go there or there. We don't know exactly where all those 42 fall, so I'm just putting them there to keep track of the fact that there are 42 single parents. Same thing with the 46 who are earning less than 40,000, and the same thing for the people living in Gatineau, where we've got 45 of them. So in this case, they didn't give us the sample space, so we don't know how many we've got in total yet. Now we're told we've got single parents making less than 40,000 who live in Gatineau, that there are 10 of those. So single parents, less than 40,000, living in Gatineau, they're meeting all 3 criteria, so we know there's 10 right in the middle. Single parents making less than 40,000, there are 30 of those. So single parents, less than 40,000, I've already got 10 of them, and I'm supposed to have 30 in total. So that tells me I need to fill in 20. Next one says people making less than 40,000 living in Gatineau. So less than 40,000 living in Gatineau has to be 24. I've already got 10 in the center, so it's 14 left. Final piece of information, single parents who live in Gatineau. So single parents living in Gatineau, that gives us the intersection point. There are 19. We've already got 10 of them there. So that leaves us with 9 in total. Now we need the people who only fit one of the categories. So for the first one, we're taking 42 minus 20 minus 10 minus 9, and we end up with 3. We have 46 minus 20 minus 10 minus 14 leaves us with 2, and 45 minus 9 minus 10 minus 14 leaves us with 12. So now if I'm going to calculate my probabilities I need to know how many people I've got in total. So I remember when I'm adding up for the total in the sample space, I'm adding up just the numbers that are in the circle. Or if I've been told that there are people specifically outside, then there might be a number here, but in this case, there's not. But I'm not adding up the main numbers that I put in brackets. Those are there to help us calculate these numbers, but they don't go into the total for the sample space because we've kind of accounted for all of them. Remember that 45 just represents everything that's in the circle. This 46 represents everything in the other circle. Same with the 42. Okay, so when we add everything up that we've got in here, we end up with a sample space of 70. So now I've got all the information I need to go and answer the questions. It says if a family is selected at random, what is the probability that the family lives in Gatineau? So what's the probability that the family lives in Gatineau, but isn't from a single family parent or from a family with less than $40,000 in income? So they're basically asking us, they're saying they've got to be in Gatineau, but they can't be a single parent and they can't make less than 40,000. So we're left with just the 12. So we've got 12 out of 70, which if you wanted in decimals is 0.1714. Part B says if a family is selected at random, what is the probability that the family does not meet any of the three criteria? In order for the people to find that number, there would have to have been a number outside here. But in this case, there was nobody there, so the number is 0. So the probability is 0. Part C says, given that the family is from Gatineau, so we're focused on the Gatineau, and we can even go so far then as to say, okay, the denominator is going to be 45. So we've taken the from Gatineau. What is the probability that they're from a single parent family? So now we take everybody that's in the Gatineau circle that's also in the single parent family. We see there's 19 of them. So we say there's 19 out of the 45. And if you want the decimal, that's 0.4222 repeating. And finally, part D, given that the family earns less than $40,000, what is the probability that they're from a single parent family that lives in Gatineau? So given that the family earns less than 40,000, so we know they're in the 40,000 circle. So I can then set the denominator to be 46. What is the probability that they're from a single parent family that lives in Gatineau? So in that case, then they have to be in all three circles. So I've got 10 out of 46, which is 5 out of 23, which if you want to convert to decimal is 0.2174. Okay, then we'll move on to question 6. So high school guidance counselors following up with recent graduates to find out where they ended up after school. Some went to CEGEP, some went to trade school, and some joined the workforce directly. Here's the information that was collected on 220 graduates. So that's the first useful piece of information I get is I've got 220 graduates. I'm going to add that to my table. 112 students are male. So that's just straight up out of the total. There's 112 that are male. And it's not a big stretch then to go and do the math right away and say, well, if I've got one gap there, I'm going to go ahead and say there are 108 that are female. Now, the probability that the student joined the workforce directly is 3 out of 22. So if I've got 3 out of 22, and that's based on the total number of people that I talked to, I can say then that I'm looking for 3 out of 22 times 220, which is 30. So the number of people that joined the workforce directly, we can put into the table at 30. Next piece of information says 70% of the students went to CEGEP. So 70% went to CEGEP. Again, that's helping us here with the total. So 70% is 0.7 times 220, and that's equal to 154. So we can add that to the table. Now we're given that the graduate is female. The probability they went to CEGEP is 7 out of 9. So we're looking at the female line. We've already got the 108 in the total. So we can actually go ahead then and say, taking 7 out of 9 times 108, which equals 84. I can go ahead and do the math then. 154 minus 84 is 70. So there are 70 males went to CEGEP. I can also figure out how many went to the trades in total by doing 220 minus 154 minus 30, and I end up with 36. Now I use the last piece of information we're given. The number of males that went to trade school is the same as the number of males who joined the workforce. So they're telling that this number is the same as this number. That helps me because I can take the 112, subtract 70, I get 42, and I'm going to divide that by 2, and I get 21. Once I've got the 21 there and the 21 here, I can subtract 21 from 36, get 15, 21 from 30, and I get 9. So I've got all the information filled out in the table. Now we're saying, given that the student is female, what is the probability they join the workforce? So I did more. Well, actually, I think I need to do almost all of that to get the final answer here. I've got 9, and because we're talking about we're given that the student is female, I know the denominator is going to be 108, and my numerator is going to be 9. So that's my final probability. If you want it in decimal, it can be 0.0833. Question 7. The game requires a player to first flip a coin and then spin a spinner. The coin has the same likelihood of showing heads as it does of showing tails when it's flipped. The spinner has 3 colors, red, blue, and green. The green takes up the same amount of space as blue and red combined. The player wins if they flip tails and then spin red, or if they flip heads and spin blue. All other combinations lose. So a few key things to get out of that. The probability of green is equal to 0.5 because it takes up the same amount of space as blue and red combined, so it's basically taking up half the spinner. Probability of blue is equal to 0.25 or 1/4, and the probability of red is also the same, 0.25 or 1/4. So I've got the probabilities. I also know when I'm flipping coins, I've got a 1 in 2 chance, so I'm going to add those. Now I can put all the probabilities I just calculated onto here. Okay, so I end up with all the probabilities that I need. Now I'm asked, what is the probability of winning? Well, what are the paths that give me a winning strategy? I can either flip heads and spin blue. So I've got to go to heads and blue. They can flip tails and spin red and win. So that's the strategy. So those are your 2 winning strategies. So you can either, the probability of flipping heads and blue is 1/2 times 1/4, which is 1/8. Or we can flip tails and red, flip tails and spin red, and that has the same probability of happening, 1/2 times 1/4, 1/8. So therefore our probability of winning is just adding those 2 together, which if we add 1/8 and 1/8, we end up with 1/4. So the probability of winning is 1/4, 1 in 4 or 0.25. Part B says, what is the expected gain if it costs us $5 to play and winning pays $10? So our expected gain is equal to our probability of winning times our net gain plus the probability of a loss times the loss. Our probability of winning, we said, was 1/4. Our net gain, we get $10, but we spent 5 to play, so we have to subtract that, 10 from 5, or 5 from 10. Then we add the probability of the loss, which is 3/4, times the loss, which is -5. Multiplying that out, we've got 10 minus 5 is 5, times 1/4 is 5/4. We've got -5 times 3 gives us -15/4. 5 minus 15 gives us -10/4, and if you divide that out, you end up with -2.5. So the expected gain, or in this case, the expected loss, is -$2.5, or a loss of $2.50. Net gain, that's the cost, it's the amount that you win minus the cost to play. So it costs us $5 to play, and if we win $10.